Good evening, everyone. My name is Yossi Levanoni. I'm a manager with DynamoDB. I'm responsible for the storage layer of DynamoDB, which is where all your data actually travels to and then comes back when you ask for it. So I've been with the team for 3.5 years now, and been involved in basically all of the features that we brought to you over this time frame. And yesterday we announced transactions. Today we announced on-demand consumption for DynamoDB. All of these are features we're very, very excited about, and I'm here to tell you more about transactions. So that was me. Now, about what we're going to go over tonight is first, what does ACID mean for DynamoDB? You have an API, you have a RESTful API that allows you to get and store and set data. What does ACID mean in the context of a NoSQL database such as DynamoDB? And how does the transactional API changes that picture? And after we get introduced to the new API and kind of see how it fits with the rest of the API that we have, we're going to go over use cases of using transactions with the new API. And then we're going to go over like important things that you need to know when you're integrating with this new API, how it works with the other features of DynamoDB. And the things I'd like you to take away from this discussion is basically how does this API works, how it fits into our tenets of NoSQL scale-out database, and what does the API look like, how you use it. We're going to go over some design pattern that will show you like good examples of how to use it. And basically also, you're also going to go out with the working knowledge of how it interacts with the other features. And why all of this is important is we have basically two main reasons. What would you like to do with transactions? What is the utility of that? The first use case is pretty obvious. You know, you have something transactional in the real world, and you want to express it in your code. So, you know, the most obvious example is financial transaction. I want to transfer some money from here to there. That's a transactional thing. You want to implement it with a transactional facility. But you know, there's also a lot of usage, and we think possibly more usage, that is just related to how you implement a cloud application. You have to store data in multiple locations. You have to, you know, put it here and here, modify something here and delete something there. All of that you can now do with much greater ease with the transactional API. The transactional API allows you to do things in a transaction with all or nothing semantics, isolated from everything else that happens. And that means that you don't need to take care of all of the you know, partial success and failures that you could have otherwise when you issue multiple requests to DynamoDB. So we go over examples that show both of these use cases. And so in order to kind of benefit from this discussion, I assume that you have some working knowledge of DynamoDB. We will not go over some basic concepts such as what are tables, how do you index into tables, what are streams, time to leave feature. I assume that you have some understanding of those. I may go over them very briefly. OK, so let's dive right into the API and see what it looks like. So we're basically introducing two new APIs. One is transact write items, and the other is transact get items. And as the names imply, one affects changes, and the other allows you to read state transactionally. So when we look at transact write items, it's limited to 10 items. These are basically items that you choose as the targets of your transaction. Now, once you choose those items, you have to decide what you want to do with them. Typically, you want to evaluate some state, make sure that some invariants are true about the things that you want to change. Once all of the conditions that you specify are met, all of the changes that you specify in the request are going to be affected atomically, completely isolated from everything else that's happening in the system. So that's basically how transact write items work. And transact get items is similar. You specify up to 10 items that you would like to atomically read, and we will take care of giving you an atomic snapshot of these items. Okay, so these are very simple building blocks, and that's what we're going to be working with. All right, so here we have a kind of a comparison of what we had before, all the APIs in the lower row versus the 2 new APIs in the top row. And then we also classify them basically into non-transactional and transactional. So let's look at the transactional column for a second. We have the 2 new APIs, transact get items and transact write items. And then we also have existing APIs that are also transactional. Get item, put item, update item, and delete item. All of the singleton APIs in DynamoDB are transactional, but they are transactional in the context of a single item. What does that mean? It means that today, using these APIs, you can read an item, evaluate a precondition on the item, and then atomically store a new value. And everything that you would do in the context of a single item will be completely serializable and isolated from everything else that you do. Atomicity means that everything that you do is all or nothing. If I read an item from DynamoDB or write an item to DynamoDB, this always happens as a single unit of work. You'll never see somebody change some key value pairs and somebody else change some other key value pair, and you see a mix of that. So atomicity and consistency and isolation at the item level, we're always there. What the new transactional API brings into the picture is that now you can do that for multiple items. So instead of doing that one at a time, you can now check the state of multiple items and change them all together or none at all. So if you compare that to the batch APIs that we had before, we still have them. It's a batch get item and batch write item. These are also multi-item operations. However, they're more like macros over single item operations. They're just basically about the efficiency of interacting with the service. So suppose you want to do multiple puts and deletes, you can group them together in a batch write item. And notice the singular term, right? It's a batch of write item requests. And then the service will basically work through the batch. We'll do it in parallel, so it doesn't take a lot of time. And some of the writes could succeed and some of the writes could fail because it's not transactional, okay? So, suppose you wanted to just load data into the database, you would probably use batch write item because you can redrive typically, and you don't really need transactions for that. But if you wanted to, let's say, coordinate a change that must be consistent across 2 items, that's when you would use the transactional API. Now, when we look at query and scan, these are also multi-item operations. They are not transactional. When you query a certain partition key, you could get results that have been created by concurrent transactions. You always only read data that has been committed and stable. You never read dirty data. But queries and scan basically give you some sort of a fuzzy read-committed picture of the database. And again, each individual item returned by query and scan is always atomic with respect to writes. Okay, so now after we talk about how those APIs behave, let's talk about the scope to which you can apply the APIs. And one thing to know about the transact write items is that you can apply it to any 2 items in your account. They can be from different tables. They can be from the same table. They can be from the same partition key. They can be across different partition keys. Any items, up to 10 items in your account in the same region, you can transact using these APIs. And the scale characteristics are pretty much like the rest of DynamoDB. You can have limitless number of concurrent transactions. It's a complete kind of scale-out architecture. And the only thing that you basically have to worry about is to make sure that you don't have hotkeys in your design. That's not a good idea without transactions, because when you are bottlenecked on a physical resource that has to basically take all of your writes or all of your reads, then you inevitably gonna reach some scalability bottlenecks. And that's doubly true for transactions. You know, if you have multiple items that are hot inside the transaction, it's very likely that it's going to collide with other transactions, concurrent transactions, and that's not going to give you what you want. So basically, you know, it's exactly the same design consideration that you have to worry about with transaction and non-transactional design in DynamoDB. Okay, so let's talk a little bit about some of the design decisions that we've made and why we've made them, how they worked towards achieving your goals. So first thing, like I said, we transact any items in your account. Why did we do that? Well, basically, DynamoDB is a fully managed database. You don't have instances. You don't have any resource governance that you have to worry about. Now we've released on demand. And basically, you can just go at it and put your load on the, on the database. So when you think about it, we just want you to bring your data to DynamoDB, scale it across this key space. You can have practically limitless amount of data. Now, how you relate the data in your application is completely orthogonal to how the data is stored. So that means that logically, you may want to relate any two items that are stored in DynamoDB. Right? You know, suppose you have a payment application, you cannot predict which two persons would want to transact with each other. So similarly, we allow you to involve any two items in a transaction. Second thing is service API versus client-side library. So as many of you may know, we have a client-side library already for transactions, and we think that the new service API is a great improvement relative to the existing library. And there are some obvious reasons. You know, you don't need to integrate with the library, and it simplifies your application. But beyond that, when you think about how transactions are implemented, you know, eventually there is some sort of bookkeeping, and the client library essentially moves all of the responsibility to you in how it manages bookkeeping. And if it doesn't work as expected, if it leaves locks abandoned, then you eventually have to take care of that. So there's also operational overhead when you work with the library. And finally, and very importantly, there's also cost and performance implications. Because we implemented transactions close to the data, we can do that much more efficiently than is possible in a library. So this is why we think that, you know, this deserves a service API. Now, when we look at that API, it's a request-response-based API. If you've worked with SQL, you are familiar with the session, conversational-based transactional model. I tell the database, begin transaction. That transaction is now active on my session, and I can query state, and then I can set state, and then I can query more state and set more state, and eventually I can commit or abort. We have opted to implement something that is API-based and is a request-response model. So we've done that because that's the pattern that works the best when you think of what NoSQL really excels in. What are the tenets of NoSQL? So the tenets are your data is large, your workload is well distributed across that data, and you want to get in and out very, very quickly. So we don't want complex logic in the transaction processing. You need to, in your application, decide what are the invariants and the state transitions that you want to affect. And then you basically summarize that in a request. And you say, I assume that the state of the world is X. Please change it to Y if it is still X. And that means that the database essentially contains almost no logic about why your application decides to do certain state transitions. The application logic stays with the application. You only tell the database, if the state is such, I want to move it to this state. So that allows you to evolve your application and not bury all of that logic in the database. Finally, the limit of 10 items also was put in place to ensure exactly those tenets of NoSQL. You want to get in and out quickly. You want to make sure that everything has predictable performance and predictable cost. And we also found that, you know, pretty much all of the scenarios that we looked at that were good NoSQL representative workloads didn't really require more than 10 items. You know, it's not about scanning your database and then changing something transactionally at 10% of the items. For that, probably you want to do something that is not transactional in nature. This is really about coordinating just a limited amount of items. OK, so having introduced you to the API, let's go dive into some use cases. So the first use case that we're going to talk about is user profile management. So suppose you have a mobile app, a web app, and you have a business constraint that you want to identify users with usernames. That's how you want them to register with your app that they choose, a username that they choose. And you also allow them optionally to specify an email. And that email can also be used to identify the user. So you want to be be able to say, hey, tell me either your username or your user or your email, and I will identify you with either one. And then we also add the scenario that we want to allow users to change their email if they choose to do so. So what we're going to be demonstrating is that with transactions, you can now effectively enforce uniqueness constraints across multiple fields, not just on the partition key or the primary key. And that allows you to also create materialized indexes based on your choice of values. And finally, we will put basically both the table that is indexed on the username and a materialized index that is indexed by the email. We'll put both of them in the same DynamoDB table. So DynamoDB table, despite their names, are just collections of items that share the same primary key. You can have heterogeneous items in your table, and sometimes it's very advantageous to do so. And this example will show us why. So here's an example of some entities, some items in that users table. So the first and third items in the table are basically a profile record. And they are the master records for two users, John and Jane. And they contain basically all of the information about them, phone number, email, any other preferences. And then the second row is an alias that we add that is indexed by the email and points using the username ref column or attribute to the master profile record for John123. Okay, so now suppose John tries to authenticate to the application. He can enter an email. We would look up by email. We don't know that it's an email. We just know it's a string. We look it up by ID. And the fact that the attribute that exists is username ref tells us that that's an alias record that points to the main record. So we would then go and fetch the main record. Similarly, if he identified by username, we would go and directly see that it doesn't have the username ref. So we infer from that that's the master record. Sometimes it's, you could add a discriminator field that says what type of item it is. Here it wasn't really necessary, so you can cut down on space and storage and save some money. So let's go through some scenarios now that will show us how we maintain basically the referential integrity here between these records belonging to John. So here's the JavaScript snippet of code that shows us how we would issue a transaction that adds John to the user's database. And it makes sure that we have uniqueness constraint enforced, and everything is done in one atomic step. So basically, we have two put operations within the transact item request. So each put operation specifies the table name that it wants to target and the keys that it likes to target. And then it can have a conditional expression. So here the conditional expression that we specify for both records, the one representing the main profile record and the other one representing the alias, both of them assert that these IDs do not exist in the database. So there cannot be another user with the same name or email or a cross reference of each other that collides with any of the identifiers that John provided in this example. So if the transaction succeeds, we know that both of these records were inserted and that there is no collision. Now let's see what happens when John tries to change his email. So we will have essentially one update, one insert, and one delete. And the thing that this shows is that we want to make sure that everything that we are trying to transact still is the same as what we think it was when we attempt the operation. So we will check that the user, the main profile item, still references the email that we think we want to delete. We will make sure that the email we want to insert doesn't exist. So these are the first two items that you see here being transacted in the transact_write_item request. And the third operation here deletes the old email. Now, you will notice that there is no condition here to check that this alias record still points to John's item. If we had additional scenarios, it might be possible that we would kind of break the invariant, that if the user points to the email, then the email points to the user. So I would say that actually this sample is deficient in that, and we didn't have that condition due to slide space limitations. But basically, as much as you are defensive in your code, always checking invariants, we would recommend doing the same when you enter transactions. There is no additional cost for you to check conditions that you think should be true according to your invariants when you do transact_write_item. So any item that you think about changing, check whatever you want to do, you want to enforce about it, what you assume is true about it. It has the same cost and same performance. OK, so let's move to the second use case. In this use case, do we have any local Las Vegans here? I guess so. We're all visiting here. We all are very familiar with this scenario. We create a reservation to book a room in a hotel here. And then we want to check into the room. And that marks our reservation as fulfilled. And then we want to check out of the room when we're done. So this is what we're going to be demonstrating here. And the thing that we will demonstrate in kind of working through that, one is idempotency. Idempotency is something super important when you work with transactions and actually any state transitions that you do in a distributed system. So think that, I have a travel application. I'm sitting on my mobile device, and I'm trying to reserve a room. And for whatever reason, there are some connectivity problems. Some server took a hike, and I don't know, whether my reservation went through or not. Now, imagine what the app has to do at that time. Will it, if it retries, will it create two reservations? Is it gonna, is it gonna create one reservation? You don't know unless you have some sort of a way to express your intent. So the app needs to say, here is my intent, and here's an identifier for my intent to make a reservation. And then the entire chain of calls emanating from that point forward can disambiguate my intent based on that ID. And this is an idempotency token. That's what it normally is referred to. And we will use that in order to make sure that when I make a reservation, it is I only create one reservation, no matter how many retries I have to go through. So, and we will also kind of work through consistency and atomicity when we make state transitions. So the data model basically has three item types: guest, reservation, and rooms. I'm not making any particular assumptions about how you put those items into tables. You can put them into 2 tables, 3 tables. You can decide to put reservation kind of hierarchically under guests in the same table using a partition key with the guest name, a guest ID, and a reservation as a sort key. That may be necessary. But here we actually chose to represent it in a different way that kind of underscores that with DynamoDB, you're not limited to key value pairs. You also have sets and maps. So if you look at the guests entity, it has a reservation set. So inside the item, you essentially have a document, and that item contains a set of reservations. So we allow you to manipulate that set using condition expressions and update expressions. You can check if a string is in a set. You can insert, upsert, delete entries from a set. And similarly, you can do similar things with nested maps inside items. So the guest reservations are going to contain basically all of the reservations that the guest has made and are either pending or active. And it's also going to contain a set of occupied rooms that the guest is currently occupying. Reservation is going to contain basically the guest ID who made the reservation. And if the reservation is fulfilled, it will identify the room. Similarly, room will have an ID, will have a state, whether it's occupied or free. And it will, if it's occupied, it will say which reservation made it occupied. So here's an example of some data that we could have with this data model. So again, you know, John has 2 reservations, 500, 501. And, you know, he currently occupies room 20014. And then we have 2 reservations, 500 and 501. One is pending, the other is fulfilled with room ID. And we have a room, and the room is occupied by that reservation, 501. So sorry. Yes. So, so how do we get to the point that we have an idempotent reservation insertion into the database? First thing, you know, you go from the client and you generate a unique ID for the reservation. Essentially, that's going to be our intent identifier. And it should be unique, but it doesn't have to be fully unique. Like collisions are tolerated. You can generate something that is unique enough. When you try to insert it into the database, if it hasn't been unique, if it is in use, you will be told so, and you can react to that. And that allows you to generate reservation IDs that are maybe shorter and easier to memorize. And then you would create a transact write item request. And in that transact item request, you would have one put that is conditional on the reservation ID not existing in the reservations table. And you would also do a conditional update to insert the new reservation ID that you created into the guest reservation set within the guest's item. So this basically, you can retry it as many times as you would like. It will always have the same side effect. And you will be told by the outcome of the transaction whether you have been attempting more than once to do it, or whether there's collision on that reservation ID, or anything of such nature. So here's what the data would look like, for example, before, after John created a reservation, just one reservation, and he's trying to check into the room. So we see that the reservation is pending, and that there's no room that are occupied by John, and that we found a room, and that room is free. Now, how did we come to obtain these 3 records? Depends on you know, how you manage your inventory of rooms, and how you identify the customer and the reservation. Customer can kind of walk up to the counter and say, "I'm John," and then you would look up the reservations from their customer record. Or you could come and I say, "Here's my reservation ID," and you would, based on the reservation ID, find who's the person who made it. And separately from that, you would find the room record that you would like to put that guest into. And so these 3 items, you don't need to get them in a consistent manner. You don't need to do it in an atomic fashion. You just piece together a view of the world that you think and hope is going to be current at the time that you attempt your transaction. So, and basically then you come to the transactional API and you say, "I believe this is the state of the world. I believe that John has this reservation, that reservation is still pending, and that this room is still free. These are all the things that I would like, I think are still current, and I would like to make the state transition to this state, where essentially we now tied all of these things together and changed states. Okay, so now let's go through the checkout scenario. In the checkout scenario, we start from where we were after John checked in. And I highlighted here the only thing that we really need to check in order to make sure that everything is still at the state that we believe it is. So if that reservation, if you'll see the second row, the reservation item, it says that the reservation is fulfilled, the customer ID is John, and that the reservation has been fulfilled by that room number. Now, if we just know about the scenarios that I outlined to you, that is the only thing we need to check. But imagine we introduce additional scenarios into the system, such as I could move a reservation from one person to another, or I can cancel a reservation, or I can move a customer from one room to another on the same reservation. If we introduce those scenarios later on, then just checking the state of the reservation and not looking at the rest of the state of the world, it can result in some corruption of application invariance. So again, we recommend check everything that you think is true. Check all of the referential integrity of these things and all of the states and make those guarded transitions as you should. Okay, and this is essentially how it would look like after the checkout. We remove the reservation from the set, the room from the occupied room set, mark the reservation is closed, and the room is free again. So now let's talk about some design considerations when you're integrating with the transactional API. And time permitting, I think we're going to have time afterwards. We're going to go over another use case. Okay, so let's talk about concurrency control. So what is concurrency control? Concurrency control is the set of mechanisms, algorithms that we implement in the backend in order to give you the ACID semantics of transactions. So basically, you want your atomicity, all or nothing. You want your consistency, the state transitions to be evaluated, again, in an atomic fashion, and the state applied in one atomic step. You want isolation, which means that the transactions appear if they never interleave with each other. And you want durability. So when you think about how to implement those properties, there's basically two choices. One is optimistic concurrency control, and the other is pessimistic concurrency control, which involves locking. Now, because we're talking about the NoSQL database, the path of success when you're using this technology is, again, to use vast horizontal scale-out with lots of operations that do not conflict with each other. So already we know that if you're using DynamoDB properly, you should not have contention between all the concurrent operations that you operate within the database. And that means that in order to get the best performance and cost and throughput, we would opt to use optimistic concurrency control. So optimistic concurrency control really assumes that there are not going to be conflicts. They handle conflicts. You're always assured that ACID properties are fulfilled, but that's going to be the exceptional case, and we're going to handle it in the back end no matter what. Any concurrency control that we would have chosen, that would have held true, but that works best when you already adhere to the design patterns that are most encouraged with NoSQL. So again, your responsibility is just to design for scale out. The same guidance that we have always given on how to work best with DynamoDB continues to apply. And, but something that is unique for transactions is to avoid unnecessary conflicts. So, you think you want a piece of data that you could read in a transaction, or you could read outside of a transaction, or something that you don't have to really modify within the same transaction and could be a source of contention, then it might be a good idea to not do that in the same transaction. So there is some sort of a trade-off here that you really need to evaluate between your ease of use, and that gives you, the atomicity gives you, versus increased contention in your application. Okay, now when it comes to metering transactions, we've seen that the way the API works is that you essentially group together either puts and puts and deletes. There's also another thing that you can put inside the transaction called conditional check. You would use that when you want to make sure that a condition on an item that you're not modifying is met within the transaction before you move ahead with state changes. So anything that you would put within a transact right item essentially is going to be metered as twice the respective metering that we would do if it was a singleton operation. So why is that? Let's think about it. So basically, whenever you're dealing with transaction, there's always a two-pass over the data. You want to prepare something, and then you want to commit it. Or if we're talking about optimistic concurrency control for gets, you want to read everything and then read it again and make sure that nothing has changed. So this is directly kind of a result of implementing transactions. There's no real kind of way of avoiding that. So we really only metering for the use behind the scenes that happens when you have to implement transactions. So let's take an example. Suppose that I have two items in my transact right items, and one of them is 1K, and I would want to do a conditional check on that, and then I want to update an item that is 2K. So 1 plus 2 gives us 3 WCUs, write capacity units, and double that by 2, that would be 6 capacity units that are going to be consumed by that transact right item request. And if you use on demand, which we just announced today, then it's basically the same thing. 6 write units are going to get consumed by that API call. Now, the nice thing about transactions is that it just fits into the existing capacity models. Auto scaling works and is recommended if you're using provision capacity. If you're using on demand, it just works and it fits into the rest of your consumption. Okay, so now let's talk about the cases where your transaction didn't go through. So, if you design for scale and you provision appropriately, or you're using on demand, and you put the right permissions, everything should work just fine. But in some cases, things are not going to work as expected, and there are different kinds of failures that can happen. The most interesting one for us to discuss are basically precondition failure and transactional conflicts. So precondition failure is very obvious. I assume that this was the state of the world. I go into the transaction and the state of the world has changed. Why did that happen? Typically because the write changed the state of the world from under me. Maybe I wasn't too careful in validating that that's a very recent snapshot of the state of the world. It might be the case that in your application, it may make more sense to first try and see that something isn't what you expect, because 99% of the time it is. Or it could be that within the transaction execution, while the transaction was executing, there was really a different transaction or a write that were colliding with your transaction, and that will result in a transaction conflict. Now, sorry, let me go back to that. Whenever that happens, either the precondition is not met, or you get a transactional conflict. If you specify that you would like to get the current state of the world, within the response, you can see what is the current state of the objects for which the conditions were not met or that had transactional failure. And then you can use that to recompute what you want to do. Okay, so we talked about idempotency that you can build into your application. Now, we also have a mechanism that's built into the SDK that is super useful to ensure idempotency for really simple scenarios where you don't want to create an intent to represent what you want to do. Here's an example. Suppose you have a voting application, and you want to just say, hey, that person voted for that singer, okay? It's some sort of, like a talent show or something like that. And you don't want to kind of keep the ID of everybody who's already voted. You basically just want to say, let me increment a counter by 1. That has pitfalls in itself, and if you catch the show by Rick Houlihan, my colleague, he talks about basically how you can distribute counters, but let's keep it simple for a second and just say that's what you want to do. You just want to increment a counter by 1, but you don't want to increment it by more than 1. But you don't want to really, make a lot of effort to ensure that. You just want to make a best effort to ensure that you're doing it once. So for that, we have something called a client request token. You can specify that in your call to the API, and it is specified by default by the SDK. And that makes sure that as the SDK retries if there are any problems, then the same client request token is specified again and again. On the server side, we will disambiguate your request based on the client request token. So if you make the same identical request within a span of 10 minutes, we will assume that that was the same intent, and we will only affect the transaction once. So, so suppose your SDK had a failure, it retries again, the service says, okay, that transaction actually failed, you get back a response that indicates that. Similarly, if the transaction succeeded, you will get an indication of that. That also allows you to have two clients that are trying to drive to the same end state, and they're competing with each other. And you see that the end state was reached, and you don't know who actually succeeded in doing it. You can use the client request token. You can, when you issue the request, it will tell you whether it was you who succeeded or the competing transaction. Okay, so if you don't use the SDK, we recommend specifying that token. And just remember that if you have something that requires intent longevity of more than 10 minutes, then probably you want to take care of it also in your application and design for idempotency, as we showed in the reservation example. Okay, so we talked about that. Let me just recap very quickly. So, if the SDK exhausts its retries and you have now to decide what to do, you have an option, right? It really depends on your scenario. So if we think about, let's think about the user profile example. Suppose we have a request to delete the user's records. And once we do that, we see that the transaction failed because there was a competing request to change the user's email. Now, at that point, the application could do one of two things. It could say, hey, according to my business logic, I should just delete the profile anyway. So let me gather the current state and redrive a new transaction. Or it could say, no, I'm not sure anymore what I need to be doing. Let me surface an error back to the user and let them decide whether, given the new things that happened, what they really want to do is to delete the user or keep it. So that really depends on your situation. But if you do want to redrive a new transaction, you need to gather a state of the world again. You can either do that with a transactional transact get items that gives you everything in a snapshot. You can compute your state piecemeal and assume that it's consistent. That might be what works best in low contention situations. And you can also use the state that is returned by a failed transact write item request if you specify return values on condition check failures equals all old. That will tell us to give you what we think is the current state. Okay, so these are basically all of the basics that I wanted to cover about how the API works. Now let's talk about what happens when you look at data that has been transacted when you're using other DynamoDB features. So DynamoDB, we have the normal write and read path. And then there's a bunch of features that are all based on the notion that we basically push data to eventual consistent data sources or pipelines. So streams is an example. You affect some changes in DynamoDB, be it an insert, an update, or a delete. And if you have streams, then you are getting essentially all of these records that you can consume and tell you what happened. Now, streams are designed, like DynamoDB, to be scaled out. And that means that streams are sharded. So the same way that a table in DynamoDB is partitioned behind the scenes, streams are also partitioned because a single client cannot read a stream where you have 1 million modifications per second, which some of our customers do, right? So we also need to shard the processing of streams. So because we allow you to transact any 2 items in any table, and we still want to have kind of a sequential order or history for any given item, we basically want to show you, allow you to, when you process the streams, to have a lineage. It's possible that you will include in a transaction items that end up assigned to completely different shards. So when you read the data from the shards, you will see, oh, OK, here's an item that has been written. And maybe a few milliseconds later, you will read another item from another shard, and you'll see that item has also been updated. Those 2 items could have been updated in the same transaction, but the way you would observe it is dependent on your shard processing. And in a scale-out system, there's really no way that you can kind of guarantee that you see them all at once across shards. Backup is kind of similar. We write those, when we decide to commit a transaction, those commits kind of quiesce in the database. They're totally durable. Any get or transact get items that you will do will see them in an atomic fashion. But when you think about backups, that's basically a global operation. And that cannot be done atomically in a scaled-out system, pretty much like stream processing, very similar reasons. So when you you take a backup or you do point-in-time recovery on a given second and you restore that table, you may see writes that have been part of a transaction. And some of the writes that were part of that same transaction are not going to be reflected in the restore table. So keep that in mind about backups and streams. Global secondary indexes are a mechanism that we offer to index on other attributes in your data. And that is also an eventually consistent facility. Again, similar to streams, we first perform the write, and then asynchronously we propagate the write into indexes based on the content of the item. So again, that is done asynchronously and on an item-by-item basis. And that is also going to be eventually consistent with respect to transactions. Global tables use a concurrency control mechanism for replication between different regions, which is last writer wins. And by default, we do not allow transactions on global tables. You can and ask us support to enable transactions for global tables. But again, keep in mind that similarly to streams, and all the other kind of async data propagation mechanisms, this is going to happen asynchronously and on an item-by-item level. Now, DAX is our accelerator. It's a write-through cache that you can put on front of DynamoDB that allows you to handle cases of high read load. Specifically, if you have very popular items that you want to increase the write throughput for particular items, DAX could be a good solution for you. DAX support is coming. It's not released right now, but stay tuned. It's coming soon. All right. So in terms of permissions, similarly to metering, actually, we don't introduce any new access control requirements on calling the API itself. The way you would authorize whether someone can update or delete or check a condition within a transaction is all done using the permissions that we already have for individual operations. So, if, for example, I have permission to delete, but I don't have permission to update, and I try to do a transaction that includes both of these operations, the transaction as a whole will fail, and the responses are going to tell me that I don't have that particular permission that is required for that operation. Okay, so we have about 10 more minutes. Let's breeze through an interesting use case. Imagine that you have a social media website where users can post and they can attach media to their posts. And what you want to do is you basically want to put the videos or whatever it is in S3 and include some sort of reference from DynamoDB. And you want to make sure that there is kind of correct state management between DynamoDB and S3. You want to make sure that if a post points to an attachment, then that attachment is there. You want to make sure that when no post points to an attachment, then we can delete the attachment. And you also want to make sure that you're not creating those attachments unnecessarily when media is shared. So you want to take advantage of the fact that users might be interested in the same media, including the same media in the same post. So you want to be able to use the same storage for the same attachment. So we have kind of a many-to-one relationship between posts and attachments, and also many-to-many because a same post could contain many attachments. So I'm going to show you basically how we can use this scenario to kind of weave together these two services, Dynamo and S3, using streams and a feature that we have called time to live that allows you to do automatic expiry of items in DynamoDB. Okay, and we're also going to do reference counting in order to implement that, because that's how we're going to know when an attachment is no longer in use. So an attachment item is going to have essentially an S3 reference. This is basically an ARN of an object that we're going to put in S3. We're going to have a reference count, and we're going to have a TTL that tells us when we should delete the item from Dynamo. And what we'll do is, once the item is deleted from Dynamo, we will get notification about that in a stream, and then we can go ahead and delete the item in S3. And then post items are going to have some data, you know, the text or whatever. This is not elaborated here. What is really important is that they contain a set of attachment identifiers, which is, again, just the names of the objects in S3. Now, if you've been paying attention, this is actually an anti-pattern the way it's presented right now, because it has a ref count on an attachment item in a mobile media site, right? So what gives, right? What if something becomes very viral and everybody wants to share it? Then that ref count is going to become a source of contention. So hold that thought. We're going to come back to that. But for now, let's deal with this with assumption that sharing is not going to be very, very prolific. Okay, so what are the application invariants that we want to have? So basically, first is that the ref count needs to be equal to the number of posts that are referencing the attachment. And if the ref count is greater than 0, then that object needs to exist in S3. And if the TTL is set, and if the ref count is 0, then the TTL is set. And if the TTL is set, and then the ref count is 0. So what does that mean? It means that I'll only want to delete the item from S3 if the ref count is 0. And I only want to set the TTL to something if the ref count reaches 0. Okay, so now let's see how we basically coordinate the two resources that are not transactional with each other, S3 and DynamoDB. And we're going to, again, use an idempotency pattern. So I'm working on a post, and within that flow, I'm saying, hey, you know, take that video, upload it into your site, and link it to my post. That's the way an attachment and an object gets created in our scenario. So what I would do is I would first decide what that object needs to be called in S3. And I would come up with something that is sufficiently unique. And then I would go and I create an attachment object in DynamoDB, an attachment item that right now points to nothing. It points to what would be a reference in S3, and it contains ref count equals 0, and it contains TTL that says, hey, you know, if that item is deleted, then go and delete the item from S3. So I go and I put that item inside in DynamoDB. Now, PutItem, if you remember, in itself can be transactional, even if you don't put it in a transact write item. When I do the PutItem, I can specify a condition expression that says only do the put if the item doesn't exist. So that ensures that the name that I've chosen for the S3 object is indeed unique. So if that put succeeds, I'm now in a state that I'm open to failure. Suppose the client died, the service dies. Now we have essentially a dangling pointer to nothing. I have an attachment object that doesn't point to an S3 object, but it has a TTL. So eventually, that item is going to get picked up by TTL. We're going to delete it. And then in a stream processor, you can say, OK, let me look up this S3 object. If it exists, I'm going to delete it. If it doesn't exist, I don't care. That's fine. You know that was an attempt to create an attachment that failed. OK? So this is how you create a placeholder for what would be an attachment. Then you go to S3 and you actually upload the object. And now we know that that object is going to get garbage collected, essentially, when nobody is referring to it anymore. And now in a transaction, you can update the item that you have in, for the post and add that reference to the item. OK, so now let's say you're trying to clone the attachment. You're basically cloning the post. You're sharing it or something like that. You want to increase the reference count. You, again, will now do that in a transaction. You will look at the new post that you're creating. You will create it with that new attachment identifier in its reference set. And you would increment the ref count. And that will ensure that the reference count is increased and reflects the number of posts that are referring to it. And eventually, based on your business logic, you will decide to delete a post, and you will then delete the post and increment the ref count of all the items that are referenced from it, all the attachments that are referenced from it. Now let's talk about contention. So we said that it's an anti-pattern. What can you do? So the nice thing about it is that working with transactions also gives you a signal about when your concurrency assumptions were false. So for example, I could have a rule that says, hey, you know, if I'm trying to commit this transaction and I'm colliding on the ref count, or if the ref count becomes too large, I can just look at the value of that thing. I could then say, hey, you know, this media is actually very popular. It's time for me to create a new copy of that media and start a new attachment, right? So you can react to transactional conflict by basically provisioning more media sources, and that is going to help you also on serving that data. OK, so that basically concludes that use case. And I'd like to thank you for your time. If you have more questions about transactions or any of the new features that we released, you can contact us on the AWS forums or on Twitter. You can also find me on Twitter or LinkedIn by my name. And I urge you to go and get the Database Freedom t-shirt that we have in the swag booth, celebrating all the new databases that we releases and which give you lots of options. So thanks a lot.